As you said, my name is Andy Howard. I'm with the Rosen Center for Advanced Computing at Purdue University. We're going to talk a little bit about our community cluster model for purchasing and how Moab has helped us move forward with this. So, first and foremost, we are a new Moab shop. We just switched to Moab in about April of this year. So, and we actually just completed our conversion of our last cluster, so we are totally a Moab shop now. There we go. So again, we're going to talk about how our business model works and how we plan on using Moab to improve our processes as we move forward. So the Rosen Center for Advanced Computing is actually part of our central IT group on campus known as ITAB. And that's a little different than a lot of research institutions where they their HPC shops may be maybe a university affiliate, but not necessarily part of the core campus IT. And so we provide advanced computational resources to our researchers, and we also support the faculty and staff members in their research and improving their methods for running jobs and conducting their research. And we also do our own research and development to try and further the technologies that we use to help them with their research. So a brief history. In 1967, we became the first, one of the first academic institutions with the supercomputer, with the data core 6500. And then over the decades, we installed more and more systems. And in the early 90s, we installed a Paragon XPS system. And we used a network queuing system along with a homegrown scheduling system named NCSS. And so that allowed us to do fair share in QS. So in the late 90s, we ran a cluster of RS6000 systems and then an IBM SP2. Both of those ran PBS Pro for the resource manager, and then they also ran NCSS on top of that for scheduling. So by the early 2000s, we switched to using just general purpose Linux machines that were repurposed from our computer labs across campus. So we would buy the workstations, install them in the labs. They would see 2 to 3 years of service there, and then we would get them and turn them into an HPC resource. And so we use PBS Pro for the batch system there and NCSS so that we can maintain the same environment that researchers had on the SP2. And so this was, we started to realize that we had a various schedulers and batch systems in our environment, and tried to make an effort to consolidate those. So at this point, in 2003, the IBM SP was about 7 years old. We also use Condor for a lot of our high throughput codes, but that's only really good for high throughput work. It didn't really help us, you can't do parallel work with Condor. And we had just constant supply of PCs, but the problem is these were workstation class machines meant for students, writing papers and things, not necessarily for doing HPC work. And the other problem is, at their age, we were seeing tremendous hardware failure. 3 years old, you start to run into memory and hard drives failing left and right. And the power consumption just couldn't keep up with what newer technologies were there. The biggest problem we ran into, though, is as part of the central IT group on campus, we didn't really have a way to make large capital purchases to build an HPC resource that, wasn't free. So enter the community cluster model. So again, as the central IT, we didn't have funding for this, but researchers around campus were pulling in grants left and right to do their research. But the problem is they would like to keep their research money for themselves, and so they would build their small resources and run them out of their own labs or out of their closets in their offices. And so we decided, what if we contact all of these researchers and have them pool their money together to buy a larger resource. And the benefit of that is they don't have to worry about managing it anymore. So we set down some ground rules for the first implementation of the community cluster model. The first thing is you get in what you put out, or you get out at least what you put in. So if you buy one node, you're guaranteed dedicated access to at least that many nodes in the cluster at any given time. If you buy 100, you have dedicated access to 100 nodes in the system at any given time. And then we decided, well, what if we go a little step further? Because researchers are doing their research at different times. Some of them may see higher peaks right before a grant proposal is due, and their nodes are just sitting there idle. So if your neighbor isn't using his queue, why don't you go ahead and use it? The caveat is if they come in later and say, well, I need my nodes back, they can preempt your jobs. And again, they don't have to do the work. All that they have to focus on is doing the research, not maintaining the cluster. They don't have to pay for grad students to maintain it, and they don't have to provide space for it, which was another big thing, being the central IT asset on campus. So we could provide the data center space and all of the support for that. So this worked pretty well, mostly. Not everything worked well. The acquisition was pretty ad hoc. We had clusters made up of various processors, various generations of hardware from vendors, various interconnects. We actually had some clusters that would be partially Ethernet, partially InfiniBand. The preemption was a great idea in theory, but it didn't really work very well. It was fairly unreliable. We couldn't always count on researchers actually having access to their nodes. And the other thing is, if the faculty member didn't have the money at the time we were doing the purchasing, they missed out on that purchase. So they would have to wait until the next one. So we had a couple community clusters spring up with only 1 or 2 communities in it, and we couldn't really leverage all of the money on campus that was coming in for this research. So we couldn't build the resources of the scale we were aiming for. There was also no end to the community cluster. So the researchers would buy a node, and then they would say, well, that's my node, don't turn it off because I'm still using it. And we didn't really have a way to weed out hardware that was past its warranty. We were still running NCSS on some of these systems, and at this point it was about 15 years old. The authors had long gone, and it was becoming a pain to maintain. So we started experimenting with Maui and then Moab, along with PBS Pro as a resource manager, and that didn't really go very well. If any of you have tried to use software from 2 different vendors, you'll know that compatibility between the 2 is not always guaranteed. So we ended up using PBS Pro for both the resource management and scheduling. So we switched to version 2, which was, we went to a 5-year cycle, and we built a cluster every single year. The vendors would provide us with a 5-year warranty, so we could guarantee hardware replacements for that a period of time. And at the end of the 5 years, we told the faculty members that cluster is retired. We'll give you partial credit for the residual value of your nodes that you can use towards the next cluster, but your node's going away. We'll probably sell it to another university or donate it to other countries. And so now we switched from a capital purchase model to a service-based model, which really helped a lot with grants, because for certain researchers it was easier to get service funding than to get money for a capital purchase. And we did away with preemption. We switched to standby queue, so you can run your jobs and all of the jobs you want for beyond your queue as long as resources available, but you can only run for 4 hours. We also switched what was centrally funded versus what the faculty had to buy in. So before we were just providing the data center space, and we put a lot of the funding still on the faculty members. So now we provide all of the data center space, the storage, and the networking. We also provide the software, the admin staff, and we use the centralized university accounts. So the faculty are just paying for the nodes. Machine selection changed a little bit too. We would send an RFP to the vendors, we would get some demo hardware to benchmark, and we would also ask that the vendors guarantee the price for about 6 months so that we can ensure people can continue buying into this deal after we've made the initial purchase. The other benefit is the rest of the university gets to use that pricing on the hardware that we bought. So if another group on campus just wants to buy a few servers for their use, they can. So the selection process, while we do benchmark and evaluate the hardware, it usually ended up coming down to what was cheapest. How many cores can I get per dollar? And the cost savings that we found in this new model were actually enough that we took all of our first generation community clusters and retired them and consolidated them into a new resource named Steel. The cost savings were from just the power savings alone from some of this aging hardware. So we actually did some preparation, and then when the nodes were delivered, we got help from all of the IT staff on campus and installed the entire cluster in a day, roughly 1,000 nodes, and we were actually running production jobs by the afternoon. So we've stuck with more or less this version of the community cluster model for about 5 years now, starting with Steel in 2008, and we've tried to just keep growing larger and larger resources, if not just better performing resources. And so all of these were PBS Pro scheduled and managed until our most recent acquisition, which happened this past year. That's Carter, which is our HP and Intel Sandy Bridge and Mellanox FDR cluster. And it's managed exclusively by Torque and Moab. So at the end of 2011, seemed to be working a lot better, but we were still running into some issues. RPP, exclusive access, scalability on the larger systems. We couldn't do fair share on a single queue only. It was fair share all the queues or fair share nothing at all. For upgrades for our old scheduler, we had to take the entire cluster down in order to update it, which our management didn't like too much anytime we had to do upgrades. And we couldn't really manipulate user job submissions very easily. The other thing that we tried to do is eliminate non-value added processes. So for adding users to the system or adding users to a queue or changing queues, faculty were having to file a separate ticket for each one of these, and the time to response was a lot longer. So we implemented a usage reporting facility so that faculty could see what they're using on their system. We also added a new queue control system for faculty to log in and manage user accounts themselves. This tool alone has helped a ton with faculty buy-in. A lot of the researchers have looked at this and said, okay, that's a much easier way for me to manage my users, for me to manage my students. I'm going to buy your stuff instead of trying to run my own. So how do we measure the success of this program? So this is the number of cores owned by department throughout the university. And at the top we see, more or less what we expect: electrical engineering, physics, mechanical engineering. But it's when we get down to the bottom that we really start to get into the more interesting use cases on our clusters. We found that people from the communications group were buying in to do social networking analysis and data mining on Wikipedia articles. Our forestry group on campus is doing research on tree growth and stuff. So this chart shows the total. The yellow bar is the total research award money coming into the university, and the white bar is how much of that has gone towards our community cluster model. So you can see that we've gone from, in 1997, only a fraction of the computing research money that was coming into the university was going towards centralized assets. Now we're up to about 50% in 2011, and we expect that to grow. And this is just a slide showing how we've grown in terms of core count and processor utilization. So the other interesting thing that we've seen by doing the centralized buy-in is the cost per flop has gone down every year that we've done this, because we're able to negotiate better and better deals. We're having better and better hardware and more buy-in. You know, as you start to buy these things at larger scale, the price gets better. So we've gone from $27 per gigaflop in 2008 to about $10 per gigaflop in Carter just this year. So where does Moab play into this? So when we started to install Carter, we worked with a select group of users from campus to give them early access to the machine. We had about 15 users who logged in and benchmarked not just the hardware, but also the new scheduling system that we had on there. So part of that evaluation included using Torque and Moab versus our previous schedulers. And the question we really had for them was, does this solve our issues, and is it close enough to what we had before that you can still get work done effectively? So in the end, we found that it was pretty effective. We could do away with RPP and the fact that it really wasn't that reliable for us. The queues could span multiple node types, which was a feature that we couldn't really have before. We still do have some different node types, usually relating to the memory capacity in a system. We could do health check, which saved a ton of jobs from failures because they would just recover anytime a node would fail. GPU support starting to become a big issue. Being able to schedule those, especially since we allow multiple users to schedule on the same node. If they have multiple GPUs, you need to be able to schedule those accordingly. Upgradability without downtimes. Again, this was a big one for our management. Being able to upgrade Torque and Moab independently, and also the ability to do rolling upgrades within Torque itself. NUMA CPU set support. So our 2011 acquisition for Hanson, those nodes have 48 cores in them. So being able to have support for NUMA Affinity was very positive. We could do fair share within a queue now. So for our larger queues and our larger user bases, such as our Exceed resources and some of the larger researchers on campus, we didn't have to worry about one user hogging all of the queue. We could start doing fair share there. And submit filters are a much cleaner way for us to implement some of the pre and post hooks that we were using before. So as I said, we just completed our last upgrade from PBS Pro to Moab in October. We're still working on a few issues. We're still new enough to this that we're trying to tune some timeout values, and we're still seeing some reliability issues with the mom and server communication. But we're hoping that 4.1 fixes that with the switch to TCP exclusively. So where are we now, and where can Moab help moving forward? So we're looking at new capabilities to provide our faculty. Job status monitoring is always a big one. We're constantly trying to improve that, and also improving the submission tools. One of the things that we're trying to do is integrate better with our license management. So you can make sure that when you request your resources, the licenses are available when your job runs. We're still early on in the process of migrating our users from PBS Pro to Torque and Moab. So we're still trying to figure out what the best way to adopt some of these aging scripts to the new methodologies. We had one user who was reporting, well, QStep -W doesn't work anymore, and I have a script that depends on that. So our solution in that case was, well, you need to use checkjob for that now, and that's worked out fine. NHC has been a big one for helping prevent bad nodes from causing job failures. Now we can check to make sure that our file system's available, our scratch file systems are available before the job even starts. And if it's not, mark the node offline so that one of our staff can take a look at it. Same thing for failed memory. One of our clusters, after we migrated to Moab, we found that it was actually had a couple of bad DIMMs in it that we didn't know about. And so NHC has been really helpful in that. We're also looking at some more usability enhancements, making QSub aware of downtimes coming up. Right now, we have a MOTD and we send out communication to users, but they may not always read that. So making QSub check to see if there's a downtime, and if the job won't schedule, alert the user as to why. Again, GPU scheduling is becoming increasingly important. And more powerful scheduling policies. So just tweaking all of the knobs that we have available to us now that weren't previously available. So that's it.